In this video, we're going to find out what limit is. Let's first take a look at an example to see the meaning of taking limit. Well, what you see now is the square root of 2. With the help of a calculator, you can easily see that it is 1.4142 something, etc., with an infinitely many digits on the right side of the dot. That is a decimal expansion of the square root of 2. But have you ever wondered how we actually get these decimal expansions? The example of understanding how we get this decimal expansion of the square root of 2 actually give us a nice way of understanding what a limit is. Now let's think about the square root of 2 not as a decimal expansion but as the sign of a square with area 2. Well, given a number a, it is quite straightforward to computing a square because it is actually a times a. But the other task, giving 2, now actually if you want to find a so that a square is 2 is somewhat not in the right direction, so it is a little bit more complicated to determine. So one way that we can find the square root of 2 is actually try to approximate it using closer and closer value to the square root of 2, meaning that now instead of trying to figure out what is exactly the square root of 2, we can try to find numbers a so that a square is actually close to 2. Say for example, if you choose 1.1, then if you take the square of 1.1 you get 1.21, which is less than 2, and it's quite too far from 2. But then you try to increase 1.1 a little bit by 0.1, you get 1.2. Now the square of 1.2 is 1.44, which is closer than closer to 2 than 1.21. And then you can try to increase this a little bit more by saying 1.3. Then the square of 1.3 is now actually 1.69. It's closer than the other two to 2. And if you choose 1.4 at the side of a square, and now you have that the square of 1.4 is actually 1.96, which is pretty much close to 2. At least it's closer than the other 3 previous results. Okay, so by actually choosing sign of a square that if you take the square, the value get closer and closer to 2, then the sign that you choose will get closer and closer to the square root of 2, right? So this is actually the process of taking limit, meaning that you choose value that is closer and closer to the real value of the square root of 2. Say for example, after 1.4 you can choose 1.41, which is actually consisting of the 2 digits after the dot of the approximation of the square root of 2, and after that 1.414, for which we take the 3 decimal after the dot of the square root of 2, and so on, so forth. So the process of taking number that is closer and closer to the value that we want to compute is actually what we call taking limit. So for this, what we can say here is that the square root of 2 is the limit of the square root of x when x approaches 2. Now in this specific example, the way we choose x is a little bit peculiar. You see that every size of the square that we choose here is less than 2. So if you consider the real line numbers, then you see that numbers that is less than 2 stay on the left of the number 2. So for this we have the notion of left hand limit, meaning that you also taking the limit of the square root of x by letting x tend to 2, but from the left, meaning that x is always less than 2. So to distinguish this notation with the real limit, then we add a subscript minus right after 2 in order to understand that it is a left-hand limit. And similarly, instead of choosing value that is less than 2, you can choosing a value that is greater than 2 to approach that number, and then you have the definition of right-hand limit. And instead of using the subscript minus, now you use subscript plus. Okay, so these are the intuitive way to think about limit. Let's take a closer look at the mathematical definition of what a limit is. So the definition is, as x approaches a, the limit of the function f is a number L. If all values of f are close to L for values of x that are sufficiently close but not equal to a. And we write a limit of f of x when x tends to a is equal to L. And so we define the limit, the left-hand limit, as x tends to a subscript minus to indicate the limit from the left, that is where x is less than a. And similarly, we have the notion of right-hand limit, where the limit is taken from the right, where x is always greater than a. Okay, so that the formal definition of limit, but it's a little bit unclear what we mean by close, right? Like fx is close to L, or x is close to a. Okay, so for this, let's take a look at the following pictures. By limit of f of x when x tends to a equal L, we mean that if x gets closer and closer to a, then fx gets closer and closer to L. And by closeness, we mean that the distance between x and a, or the distance between fx and L, is small. Let me remind you that you can actually represent real number on the real line as dot. So we can actually talk about the distance between real number by just considering the absolute value of the distance of the difference between these two numbers. Okay, so if we say that x is close to a, we mean that the absolute value of x minus a is small. Or similarly for fx L. So the rigorous mathematical definition of limits should be the following. Well, by closeness, we should choose a standard for closeness, right? We'll say x minus a, the absolute of x minus a, less than 1 over 2 or less than 1 over 100. Well, that is actually the way that we define closer and so the first thing that when we choose any positive number delta that we want to use at a way to measure the closeness between fx and L, then we require that there exists a positive number epsilon, such that whenever x and a are close with respect to epsilon, meaning that the absolute value of x minus a is less than epsilon, then we require that the distance between fx and L is also measured by delta, meaning that the absolute value of fx minus L is less than delta. That's what we mean by limit. Okay, so this is the actual rigorous mathematical definition of limit. It might look a little bit complicated, but it is very useful in practice. And well, even though it is complicated, do not be afraid of this, because actually from this we can deduce a lot of more familiar and eyes-friendly rules to compute limit, as we now see. Okay. Before getting to some general rule for computing limits, we just take a look at the following remark, that the limit of f of x exists and equal L when x tend to a, if and only if both left hand and right hand limits for f exist and are the same number L. It means that if we see that the left hand limit and the right hand limit are different nor doesn't exist, then the limit should not exist. Well, now let me assure you that you will seldomly use the rigorous mathematical definition of limit to compute it, because for most of the familiar functions like polynomial 1, rational functions, exponential function, or logarithmic functions, then if a belongs to the domain of f, then the limit of f of x when x tends to a is actually fa. So this rule actually gives us a very nice way to compute limit. So for example, limit of x squared is actually when x tends to 2 is 2 squared, which is 4. The limits of 1 over x plus 3 when x tends to 2, remember that 2 actually belongs to the domain of 1 over x plus 3, is actually 1 over 2 plus 3, which is 1 over 5. And similarly for exponential functions and logarithmic functions. Okay, so for now we can compute a lot of limit functions. So in this formula, actually in order to compute limit, we require that the value a need to be in the domain of the functions. However, let's take a look at the following example. Here we are required to compute the limit of x times x minus 2 over x minus 2 when x tends to 2. Well, you see that 2 minus 2 is equal to 0, so the value 2 actually does not belong to the domain of this rational functions. However, remember that when we take limit, we do not actually let x to be 0, to be 2. So x minus 2 is not 0 at all. So for this remark, we see that the limit of this function is the same thing as the limit of x after simplifying x minus 2 on both numerator and denominator. And where of course limit of x when x tends to 2 is just 2. So you see that in this case, even though 2 does not belong to the domain of the function in consideration under considerations, but the limits exist. And we have a general rule to compute the limit of rational functions outside the domain of that functions, which is now if Rx is a rational function such that a does not belong to the domain, then we see that Rx should be written as x minus r power m times fx over x minus r power n times g of x, where f and g are polynomials such that a is not the zero of both f and g. Okay, so in this case, the limits of Rx when x tends to a exists even only if f is greater than or equal to m. It means that if m is strictly less than n, then that limit doesn't exist. And we can say more about the case where the limit exists. In fact, if m is strictly greater than n, then the limit is 0. Otherwise, the limit is the quotient of fa divided by g of a. So if you take a look back at the example that we just seen of the rational function x times x minus 2 over x minus 2, we see that a is actually 2 and m is equal to n is equal to 1. So from the general fact, we can easily deduce that the limit of that function now is 2. Okay. Now let's take a look at limits when x does not tend to does not approach some real number, but it's go to either minus infinity or to infinity. So for example, as x tends to minus infinity, the function e power x tends to 0. Well, so in this case we say that the limits of e power x as x tend to minus infinity is 0. And based on the definition of limit, we see that we can say that limit of f of x when x tends to minus infinity is L if for all delta greater than 0 there should exist a number, a negative number n, such that whenever x is less than n, then the distance from fx to L is measured by delta. And similarly, we can define the limit of fx where x tends to infinity. Okay, so let's take a look at some properties of taking limit. So suppose that the function f and the function g both admit limits when x tends to a, and the limit of f is m and that of g is n. Then the first rule is that taking limits commute with taking sum, meaning that the limit of the sum of fx and gx is actually the limit of fx plus the limit of g of x, which is now m plus n, and similarly the limits also commute with taking difference, meaning that the limit of fx minus gx is the same as the limit of f of x minus the limit of g of x, which is now m minus n. And similarly, we have the commutativity between limit and taking product, and so the limit of the products of f and g is now m times n. And if n is different from 0, we can also talking about the limit of the quotient of fx and gx, which is m over n, provided that n is different from 0. Okay. So the next property is quite simple, but is very useful in practice. It is the limit of any constant functions fx equals c is always c no matter what a is. And by substituting the constant function c for g of x, then actually we can rewrite the previous rule as limit of fx plus c is m plus c, the limit of fx minus c is m minus c, or the limit of c times fx is c times m. Okay. Now the absolute value also commute with taking limit, meaning that the limit of absolute value of f of x is also the absolute value of m. Taking power also commute with taking limit, meaning that the limit of fx power p when x tends to a is m power p. But taking root is somehow more complicated, as we have to divide it depending on the order of the root. So for example, if the order is odd, then we do not need to take care of m. We see that the limit of the 2k plus 1 root of fx is the 2k plus 1 root of m, but when the order of the root is even, then actually we need to require that m is greater than or equal to 0. Okay, so now let's take a look at some particular example. Here's we made up of very bizarre functions, x squared minus 6 all square divided by the square root of the absolute value of x power 3 minus x minus 4. The reason that we cook up this weird function is because we want to have a chance to apply most of the rules that we just depicted so far. Okay, so first, the function x squared minus 6 and x power 3 minus x minus 4 are actually polynomial functions, so we can easily compute the limit of them, which is minus 6 for x squared minus 6 and minus 4 for x power 3 minus x minus 4. Okay, so here actually we can use the fact that these functions are polynomial functions. Now, using the product rules, we see that the limit when x tends to 0 of x squared minus 6 squared is actually the square of 6 minus 6, which is 36. And the limit of the absolute value of x power 3 minus x minus 4 is actually the absolute value of minus 4, which is 4. And the limit of the square root of the absolute value of x power 3 minus x minus 4 now is actually the square root of 4, which is 2. Well, so now we just need to take the quotient rule and decide that the limit of the function under consideration is actually 36 over 2, which is 18. Okay, so now we will define the continuity of function using the notion of limit that we already defined. The function f of x is said to be continuous at x equal a if, first, f of a exists, meaning that a belongs to the domain of f. Secondly, we require that the limit of f when x tends to a or approaches a exists. And third, we require that the previous two values coincide, meaning that the limit from of f of x when x tends to a is equal to f of a. And if the function f is not continuous at x equal a, we say that it is discontinuous at x equal a. And if f(x) is continuous at each point of an interval, then we say that f(x) is continuous over that interval. Now, for example, because we already see the rules to compute limit for polynomial functions, rational function, exponential function, and logarithmic function, we can easily see that polynomial function as continuous over the real numbers. So now let's take a look at the function that is discontinuous at some point. For example, f(x) piecewise defined as x over 2 plus 3 if x is less than minus 2, or x minus 1 if x is greater than or equal to minus 2, is not continuous at x equal minus 2. For this, we just need to check whether minus 2 belongs to the domain of f or not. The limit of f when x tends to minus 2 exists or not, or in case these two values exist, then they should be the same. So there are three things that we need to consider. So first, we see that minus 2 actually belongs to the domain. Now we want to see whether the limit of f of x when x tends to 2 exists or not. For this, we just need to compute the left-hand limit and the right-hand limit and compare them. So the left-hand limit is actually the limit of x over 2 plus 3, and when x is equal to minus 2, this function x over 2 plus 3 is actually 2. So the left-hand limit of f of x is 2, and similarly the right-hand limit of f of x is actually minus 3. So these two values are not the same. It means that the limit of f of x when x tends to minus 2 does not exist. Therefore, the function is not continuous or discontinuous at x equal minus 2.